Good evening. I'm Kamala Gunawardhan, actually former chairman of the Civil Engineering Sectional Committee. Today, I would like to start the session by introducing from the resource person, but actually there is no need to, there is nothing new, but as a formality, I welcome everyone for this lecture, which is our professor is doing it very greatly, and this is again actually a continuation of the previous lecture. So reinforced concrete is commonly used as for building. So he is going deeper in this, continuing the contents of this lecture, and he will be continuing this even today. So I welcome everyone for the lecture, and Professor, welcome you as this honor with a great honor and to do the lecture. So I think with this note, I will hand over the session to Professor. It's over to you, Professor. Thank you.
So first I'll share the screen.
Okay, sir.
Right. This is what I showed last time. There's a note. Our engineer Banduk has already shared it, and it has a lot of important data, like how to create the load combinations. Then about concrete, we discussed a lot about properties of concrete, and then the design equations, why you get this 0.85 FCK divided by gamma C giving 0.567, and the limit of this rectangular parabolic region and the rectangular region from 0.002 to 0.0035. I told you these are valid only up to 60 megapascal cube strength or 50 megapascal cylinder strength. If you are going to have a bigger strength, these will be lesser values, because concrete becomes brittle as it becomes stronger. And this is the magic number, C5060. And then steel reinforcement also, we have a special situation because we are now not using 460 steel that gave 400 as the strength, or a strain of 0.002. Now we get a strain of 0.00217. In BS code, we got a strain limit of 0.002 here because we were using 460 steel having a working stress of 400. But now we are using 500 steel having a bigger working stress, that is 500 multiplied by 0.85, which is about 530 maybe. And then you get 0.0217. So those are the changes. So this has not changed. The same for BS code and Eurocode. And these BS code did not talk anything about 60 megapascal, so this was okay. But Eurocodes go up to 105 megapascal cube strength or 90 megapascal cylinder strength. So these values will change. So just keep it in mind. Don't use the same equation without worry. So you have to be concerned about it. Then we have these, cover conditions, and generally our cover condition will be XC3, and XC4 can be for bridges, highway bridges. XC3 is the normal cover condition for buildings, and XC3, if you are using anything any less than C3540, so if you are using C3037, and so here you can't do any modification if you are using C3037. Then the cover is for the normal condition is 50-year lifespan. The cover requirement is 25. But Eurocode says, you have to allow 10 millimeters for tolerances. So the cover requirement in Eurocode is 35. But if you are using high strength concrete, so if the concrete strength is more than 35, 45, reduce the class by 1. So then you don't have to look at S4, you look at S3, and you need 20 millimeter cover. So 20 plus 10 is 30. So if you are using a concrete like 50 megapascal or 45 megapascal or 50 megapascal cube strength, the cover requirement is 30, otherwise 35. So that's what you have to. It's a simple number to remember. Cover requirement is 35. Whatever it is, because we are not going to use 50 megapascal concrete for slabs and beams, it's useless. 50 megapascal is needed only for columns, so you don't have to do anything like that. So just 30 megapascal concrete that is usually used. 30 megapascal is very sufficient for Sri Lanka, but you can see the cover requirement is 25 plus 10, 30. And this is much bigger than the usual value that we encounter with BS codes, and most of the time you will find the cover requirement is 25 or 30 millimeters, and usual rule that we use is for slabs, if you want, you can use 20 millimeter cover. For beams, 25 millimeter cover. For columns, 30 millimeter cover minimum. So many engineers use the values like 25 millimeters for the slabs, 30 millimeters for the beams, 40 millimeters for the columns. So that was the rule in BS. But you can see in Eurocodes, it is 35 millimeters for all. Even in slabs, you need 35 millimeters unless you can assure that the slab is cast with special precautions that 25 millimeter cover can be assured. Sometimes it's very easy to take cover meter readings and assure that the 25 millimeter cover is there. So in slabs, if you want, you can use 25 millimeter cover, but you have to do a survey and show the 25 millimeter is there. So that is something extra. So it's much easier to just keep 35 millimeter cover in the slabs as well. So, but if you want to have a really thin slab, you want to optimize it, then you need 25 millimeter cover for the slabs, and then you have to buy a cover meter, and when you are doing the concrete, do it carefully so that 25 millimeter cover can be verified and assured. So that is the situation. But if you are doing a say 150 millimeter slab, keeping 35 millimeter cover will assure a building that will not have any problem over a very long period. Sometimes now this S4 is for 50-year design. If you want 100-year design life, what are you going to do? Slab geometry. So if it is 100-year, increase the class by 2. So you have to say not S4, you have to go for S6. Now you can see the cover requirement is 35. 35 plus 10 is 45. So but 35. But if you are using 50, so if you want a very high durability, then you will go for high strength concrete, 45 megapascal. Then you can reduce it by 1. That means S5 is 30. So that means if you want a 100-year lifespan, what you need is 40 millimeter cover. What you need is 40 millimeter cover. Otherwise, you can do a survey and assure. If you can assure 30 millimeter, then you can even use 30. So rather than worrying about all these numbers, I generally say in Eurocode, the cover requirement is 30. In slabs, you can reduce it to 10, but you have to do the slab concreting carefully, assuring 25 millimeter cover. That's a good. But if you are not going to be concerned about it, even in the slabs, you have to give 35 millimeter cover. Is that clear, Bandhugal?
Yes, sir. That is clear, sir.
That is clear, right?
Yes.
Right. So this now I think you can have a good idea how to use this table. So if you have for example, if I'm precasting a slab, so when you are precasting the slab, you have no problem. You can assure the cover very easily. So you don't need the clearance tolerance, and you can reduce the class by 1. You can reduce the class by 1. That means S3. So if you are precasting a slab, what is the cover requirement? 20 millimeters. Right? If you are precasting a slab, cover requirement is 20. If you are not precasting, 25. But when you are not precasting, better to have the tolerance 10, 35. But if you are going to verify, again you can go for 25. So because cover is the main reason for durability. So Eurocode identify this very clearly, and they have placed a lot of emphasis on the cover, especially the people doing construction haphazardly, not paying enough attention to the cover, where they don't use proper cover blocks, they don't keep enough cover. For such situations, Eurocode is very specific. They say keep a tolerance. And for bridges, you can see the cover is about 5 millimeter more. So the cover in bridges should be 40 millimeter. Cover in bridges should be 40 millimeter, whereas in buildings it can be 35 millimeter, but can be reduced to 25 in slabs, provided that you are careful. So it's not a major deviation, only about 5 millimeter extra in the Eurocode than what you have used in the British code. So it's not a major thing, but you have to keep in mind the cover is 35 millimeters. Right now, then we looked at members subjected to flexure, and then I showed you how this happens and how to derive this K factor. K is equal to M over BD squared FCK, and then this equation, and then use this equation. M is equal to force multiplied by lever arm, because this equation gives lever arm, this equation gives moment. So force multiplied by lever arm is the moment. The only unknown here is the area of steel. So you can straight away find the area of steel, and we did one example, and we showed, then I showed there's a shortcut method. You don't have to use any of these equations. Just find M over BD squared, divide by 4, and that is equal to 100 days over BD. But that is a shortcut. For any site situation, you have doubt, use that method. But don't use that method for designs. Use this method for designs. Is that clear? Right? Use this method for designs.
Yes,
but whenever, as engineers, we need rules of thumb. A lot of rules of thumb. Why? When you have rules of thumb, we can show that we are knowledgeable, right? So somebody asks a question, we don't say, okay, I have to go and do calculations and give you an answer. We just say, okay, just give me 1 second, and use the rule of thumb, get an approximate answer, and tell the people, okay, this is what's going to happen. This will need 3 numbers of 20 millimeter bars. So the people around you will wonder how this engineer is doing all these calculations in a fraction of a second, and she must be a brilliant engineer. Otherwise, how could you say the reinforcement requirement in a beam having a depth of 600, width of 300, span is 6 meters, is 3 numbers of 20 millimeter bars? And a young engineer would quickly check it on his computer program, Excel sheet, and he confirms, okay, this engineer is correct. Yeah, his answer is correct. Then the people will start wondering, how on earth you do all these calculations, but you have your own set of simple calculations. So that is called heuristics or rules of thumb. So the rule of thumb is, a shortcut, pretty accurate, not 100%, but it gives a close enough answer. When you are doing some work which needs where you have to see the big picture. Now, when you are designing a building, there are 2 levels that you can do the design. The first is the preliminary design, where you get all the general arrangement drawing properly done, with or when you are selecting the structural form to be used, the general arrangement drawing, where you look at the alternative slab systems, right? Come up with the most economical slab system. So that is the preliminary part of the design. So if you get the preliminary part of the design correct only, we can do an economical design. Otherwise, you can do a design. The moment that design is shown to a person who knows how to do value engineering, for example, I am very good in doing value engineering, and I might say, okay, don't worry, I will do this project, the structure for you at 80% of what this design has done, which means a saving of maybe 500 million rupees, provided that you give me 10% of what I save. 10% of what I save, right? 10% of 500 million is 50 million. So that's how some engineers, earn a lot of money. So there are few engineers who are really good at that, and so they earn money this way, because whenever they see an average design, they offer the value engineering solution. In value engineering, if it is a already tendered project, where the contractor comes up with value engineering, and let's say the project value is 5,000 million, the the contractor sees the opportunity for value engineering, and he says, okay, I'm going to save 1,000 million, or I'm going to do the project at 80% of this cost. Then what happens? Then the client will say, okay, I will allow you to come up with a solution on one agreement according to FIDIC conditions of contract. When you do value engineering, 50% belongs to the client. So the project cost is 5,000 million. It will become 4,500 million, because the contract is going to save 1,000 million, right? So 5,000, 80% is 4,000, saving is 1,000. Out of that, half belongs to the client. So client gets a saving of 500 million. Contractor also gets a saving of 500 million. So this 1,000 million, the fee of the value engineer is 100 million, 10%, and value engineer gets 100 million. Contractor gets a profit of 400 million. So without doing a single thing, by doing a value engineering, the contractor gets 400 million. But on the other hand, the contractor would need far better quality assurance and quality controlling during the construction. So the contractor may have to hire about 8 to 10 young engineers who will keep an eye on the construction aspects strictly, so that the optimization can be realized properly in the actual structure. Now that's how the projects like Altair was done. Altair had 24-hour surveillance at the site by young engineers. Some contractors are reluctant to employ engineers, thinking that engineers are expensive. But the reality is, if you have engineers at the site as quality assurance, quality controlling, and quality assurance engineers, they can make things happen. So when you go for value engineering will say, okay, I'm going to bring you a big profit. Out of your profit of 400 million, keep aside 50 million for the salaries of these extra engineers who are going to make it happen properly. Because we can't have, haphazard construction when you do value engineering. Value engineering means very accurate, high quality construction, which can be done by normal people, provided that there's a special team of quality controlling and quality assurance engineers who are going to keep records. And the value engineer will certainly provide all the knowledge needed, but he cannot provide the supervision. Supervision has to come by employing a lot of young engineers who can provide 24-hour surveillance. Even if a concrete is done over 24 hours, there will be 3 shifts of engineers who will take over from 8-hour shifts. So like this, you have to have engineers. You can't have one engineer doing say 18-hour shifts or something like that. You have to have many engineers doing 8-hour shifts, so that the quality controlling, quality assurance part can be properly recorded, and all the record copy keeping will be there, and you can use a database for record keeping. You don't have to write everything on paper, but everything can go into a notebook. But every day all the data is entered, and you have to have an up-to-date database. So if anything goes wrong on a particular day, all the information of what happened, including the photographic evidence and video evidence will be there. So this is a new level of construction that you need in Sri Lanka because of very high construction cost with average designs. Now many clients are seeking value engineered solutions where the cost of construction will be low, but the quality assurance scheme will be tough. So that's a way forward when we are in a crisis where the steel prices are extremely high, something like including VAT, it is about 350 to 355,000 retail. But for contractors, large contracts, they can get steel from 220,000 to 245,000 per ton without VAT. Without VAT. So VAT component is not important for most of the property developers and so on, because finally they are going to charge the VAT from the people who are buying the property. So though they pay VAT, that can be claimed back. So basically, VAT is not a problem for property developers. And anyway, the people who buy apartment had to pay 15% VAT. Now they have to pay 18% VAT. So it's not a major burden. It's only 3% increase. But on the other hand, if you do value engineering and bring the cost down drastically, say bring the construction cost down by 25%, then you can pass part of that advantage to the buyers, and finally you will find buyers are actually paying less. Though the VAT is 18%, buyers are paying less because engineers have been smart. So what we need is smart engineers in future who are very conversant with the latest advances of Eurocode, latest possibilities allowed by Eurocode. Is that clear, Bandhu?
Yes, sir. That is clear.
Very clear. So you have a lot of challenges. You can't be practicing as you have done earlier. You have to be a smart engineer who can come up with the most cost economical solution, which will allow a final product at a lower cost, where the clients who are going to buy your product will have to pay less despite a higher VAT rate. So that is the way forward, because we are in a time where we are trying to mold Sri Lanka as a developed country like Australia or England. In Australia or England, VAT is there for everything. And whenever you buy something, you get a VAT receipt. So in Australia, value engineers are earning a lot of money, because whenever they see a design, they do value engineering. And builders always go for value engineers. And when they win the contract, they get a value engineered solution, and then they give part of the benefit to the client. They keep a net profit without doing anything. Now they keep a net profit, and the value engineers are also paid in a healthy manner. And one good example is, if possible, I will try and get one lecture organized by him. And he's an engineer from Melbourne. He's running Ranjan Fernando Consulting Engineers firm for geotechnical designs. And his task is to do engineering and reduce the cost. And he told me last year alone, he has spent 130,000 Australian dollars to come to Sri Lanka, which is about 26 million rupees. So he has spent 26 million rupees on airfare alone, because he travels business class and even higher. So that's the kind of money the value engineers earn. So value engineering is something that you all should try to learn. I'll try to teach how you can do it, but it is an art. So I can teach to a certain extent, but I can't teach it 100%, because it is something that you yourself would have to develop by knowing a lot of facts about design. So, but I'll try to, the whole idea of this lecture series is to take you there. But how well you go there will all depend on how much effort you put into this. Right. Now, if you look at this X, That is the depth to the neutral axis. If you look at this S, it is 0.8 times X. If you look at Z, Z cannot be very large. Why? Z, the maximum depth is 0.8x. So maximum value of so minimum value of Z is 0.82 times D. It is given as a function of D. But sometimes you get a Z value less greater than 0.995 D, which means very little thin layer of concrete is available for capping compression. We don't like that situation. So we have a maximum limit of Z as 0.95 D. So you have to keep in mind Z has a maximum limit of 0.95 D. Z has a minimum value of 0.82 D. So that is a theory. Because that happens because X has a maximum value of 0.45. X has a maximum value of 0.45. And last time I explained why we need a X of 0.45D. Why? Because when this reaches 0.0035, this has to be more than 0.0035. Reason? Because we like steel to yield and concrete to crack and give us a warning before it fails. So, and this type of beams are called under reinforced beams. So any beam having a neutral axis less than 0.45 D, neutral depth of the neutral axis less than 0.45 D is called under reinforced beams. But if you have a beam with lot of reinforcement where XOD exceeds 0.45 D, then it's over reinforced. So what can you gather from this? Don't provide too much reinforcement. If you need 3 numbers of 20 millimeter bars, the maximum you will provide is you will provide 2 numbers of 20 millimeter bars and 1 number of 25. You will not go for anything beyond that. And what is the reason for that? So let's have a look at it. So I'm going to go to the sheet now. So let's see why we like to provide little reinforcement at certain sections extra. Some places we don't like to provide any extra reinforcement. And with that, I'm going to explain something called moment redistribution. Now, how many of you do undertake moment redistribution when you are doing the designs? How much moment redistribution that you undertake? So these are important questions. And and also I would like the beams to be singly reinforced. I would like the beams to be singly reinforced. So I'm going to explain some of those things now. Right. Now, when you look at concrete, now what do you know about concrete? Concrete is based on natural materials. Concrete is based on natural materials. Okay, so we have concrete. We have concrete. What are the ingredients for concrete? Concrete. Cement, based on limestone. Clay, natural materials. Sand, metal. So all these are natural materials. Now we mine sand. We manufacture sand. We manufacture sand. We mine sand. We dredge sand, dredge the sea. Now all these will have an environmental cost. Are we paying that? No, we are not paying the environment. We crush the metal. Fortunately, this rock is available all over Sri Lanka, so we can crush it. We can never end it. But it may have some environmental cost. Are we paying? Cement gives out carbon dioxide, so it has an environmental cost. So today is 3rd December 2024, January 3rd, January 2024, Civil Engineering Sectional Committee lecture series. Today's lecture is fifth lecture. Fifth.
Yes.
Page number 1. Right? Fifth lecture and page number 1. So all these have environmental costs, huge environmental costs, because cement production is responsible for 7% of greenhouse gas emissions. Are we paying for this? Are we? I mean, how many cement companies at least try to manage a forest or go for tree planting? We have so many cement suppliers. How many are, allocating little money to have a tree planting campaign in Sri Lanka using the school children or university undergraduates? Very few. But these are huge enormous costs. So concrete is cheap. Why? Not that it is cheap. If we pay for the environment damage, it is not cheap. But it is very, very cheap. Steel, recycle. Even the billets that you import from any country, most of the time they will have about 25 to 80% recycled content. Sometimes it can be as high as 90%. Recycling is okay because it needs less energy than making steel from iron ores. But what is bad is recycling at lower temperatures. If you do the recycling at high temperatures using steel, using electric furnaces, then recycling is good, no problem. So you'll find, most of the countries having hydropower. Those are the countries where the steel, converting steel from steel ore is carried out. In all the other countries, they do recycling. Converting steel ores to steel needs a lot of energy. But recycling needs less energy. So recycling is good, no harm. But you can do it using electric furnace, not using gas, because gas cannot give the correct temperature sometimes. So you have to do the correct recycling. And in Sri Lanka, some people recycle without using gas powered systems, which may not be the ideal. The ideal is to go for electric powered recycling. So we have two materials. On one side we have concrete. This side we have steel. Concrete is very good in carrying compression. Concrete is very good in carrying compression. Steel can carry compression or steel or tension. Steel can carry both. Now, so my perception is, if concrete is good, use concrete to carry, because concrete is cheap, use that to carry compression. Use steel only to carry tension. To get a situation where you have to doubly reinforce the section like this. What is the meaning? What is the meaning? Meaning is wasteful design. Design by selecting a too small section at GA level, general arrangement. At GA level, you have selected a too small section. It's not good. It's not good. So how do you do the selection? Okay, when you do a design, say, let's say this is the grid, this way 7 meters, this way 6 meters. So we are going to use a slab of 160 millimeter. Now again you will ask, why 160 is an odd number? Now why odd? Now you can have 90, 100, 110, 120, 130, 140, 150. 160, 170, 180, 190, 200. Now, what are the thicknesses that you use? Use 100, use 125, odd numbers, 150, 175, 200. Why? Those are odd numbers. Those odd numbers have come from the imperial system. Now we are in the metric system. We have to get rid of this imperial system-based mentality. Okay, so use 160 or 170 rather than using 175. So because the deflection has to be satisfied, because there's a span of 6 meters, there's a possibility of satisfying this deflection criteria using 160, but 170 may be preferred, because then you can reduce the amount of steel needed. So let's say 160 or 170. So that means, what would I know? I know, let's say I'm using 170 multiplied by 25 is the dead load, and then I would have 1 kilonewton per meter squared for finishers, services plus finishers, and another one for partitions, plus an imposed load of 2.5. Then I can calculate what is 1.35 GK plus 1.5 QK, which will come to about 12 to 30. So you calculate them. So immediately you know the value 12 to 30, and you know in this slab the loads are going to come like this. So it is so this is going to get more load. This is going to get the 7 meter is going to get more load. So the load on 7 meter span is 13 on this side, 13 into 3. So 39 comes from this side, 39 comes from this side. So I have considered this value is 13. 1.35 GK plus 1.5 QK is 13. So if it is 13, 39 will come from this side, 39 will come from this side, but because it's trapezoidal, I'll say 80% of 79 will come. 78 will come. So the load will be about 65 kilonewtons per meter. So with some simple calculation, you can straight away decide what is the load that is going to come onto this beam. So it is 65 kilonewtons per meter. So this page number 2. So 65 kilonewtons per meter. So what do? Then you will say, okay, page number 3, 65 is going to be a continuous beam. So you get a bending moment diagram like this. So this value will be about WL squared or 10. So it is 65 multiplied by 7 square divided by 10. Bandhu, what's the value here? 65 into 7 square divided by 10.
1 minute, sir.
Yeah.
We have 318.5.
318. So let's say 320. We are doing approximate calculation, right? 320. Now let's say I have selected a beam, right? And the beam is 300 wide, 600 deep. So what is MOBD square? 320 into 10 to the power 6 moment MOBD square. Breadth is 300, depth is 545, 35, 45. What is the value of the
3.59.
3.59.
59.
So if it is less than 3, it's very good. Because if you look at that chart, you see that these values are pretty comfortable with values like 3, because it's in the straight motion. So what I do is, now I'll select 350. Now what will happen if I select 350? 600. So what is this MOB discount? So you divide it, multiply it by 300 and divide by 350. You get 3.2.
3.2.
Yeah, 3.2. So that's good. Even 3.59 is not a problem. Why? Because this is not going to behave as a rectangular beam. This is going to behave as a flange beam. So that means, what is the reinforcement arrangement? Singly or doubly? Singly. No reinforcement needed at the top because it's a flange beam. So that means this can be used, which is more economical. Maybe this is more economical because it's going to behave not as a rectangular beam in the span, it's going to behave as a rectangle. It is going to behave as a branch beam, right? Is that clear?
Yeah, yes, sir.
So you would have seen all these rules of thumb given by various people. But what is the, I select the general arrangement. I select the general arrangement drawing so that all beams will be singly reinforced. Why? Doubly reinforced beams are very expensive. What is the reason? For concrete, we don't pay for the environmental cost. For manufactured steel that is imported, there's huge amount of steel energy component in it. So steel is very expensive. It is very, very expensive. 1 meter cube of concrete can be made for 22,000 rupees at the site without transportation, right? For the as the material cost, I'm not talking about labor cost, right? 22,000 as the material cost, right? But 1 ton of steel, it varies without VAT, 220 to 245,000 per ton. For what? For the people who are doing contracts, big contractors, they can get steel at a low price because they are purchasing huge quantities and manufacturers will give the biggest benefit, including the advertising cost, because there is no advertising cost. Whereas when they are selling the steel, they are competing in a small market with many players. So there will be huge advertising cost. So the including that, 1 ton of steel will be 355. Can you see how the numbers vary? Banduk, if the steel is 245,000 with 18% VAT, what is the value? If the ton of steel is 245,000 with 18% VAT, what is the value a contractor will pay? You have to multiply 245,000 by 1.18. What is the value?
289,100.
Yeah. So something that the contractor gets for 289,000,
Yes.
a normal house builder pays 355,000. But for the construction, the contractor, it's VAT free. So they get it at 245,000. Whereas the VAT is paid by the client. And client will finally recover the VAT from the buyers of the apartment or buyers of the building. Will have to pay the VAT. Okay. So you can see for contractor it comes at 245,000. So that's why sometimes the apartments can be sold at a very competitive price than a house, because apartment you have say 60 perch land and 80 apartments. So the land value is divided by 80. So the land value component is very low, and it is done by a construction firm where VAT is not included in the cost. So finally, VAT is recovered from the buyer. So even if the buyer pays 18% VAT, if the engineers are smart, they can make a product which costs less. And finally, you'll find buying an apartment is far more profitable than buying a house or buying a block of land and building your own house. Now, this will all happen if the designers are smart and they know these facts. When the building is designed, all the beams are singly reinforced. No beam is doubly reinforced. Is that clear? Now, I'm gradually coming to value engineering.
Yeah, yes, sir. Clear, sir.
Right? So, is that the way you would have thought earlier? I mean, have you thought about the final product, or you would have thought about the completion of a design? I'm sure most of you would have thought about completion of design, but not the value engineering component in it.
Yes,
So
sir.
the
Most of the
engineers
time,
do value engineering, yeah. Most of the time, you want to find the reinforcement. You are not interested in finding whether
yes,
it's the optimum solution. Is that right?
correct, sir.
Yeah. So, but you have to now think differently. Why? We are in a crisis. We are in a crisis. In a crisis situation, what we need? We need innovation. So, I'm talking about innovation that you can actually use. So, that's the important thing. Okay?
Yes, sir.
Right. Now, let's see the next part. Now, I'm going to come to another very important aspect of structural design now. Now, let's say we have a beam. 6 meters, 7 meters, 6 meters. Now, you might ask why I selected 7 meters for the middle. Actually, when you have 3 span, if you make the center span slightly bigger, it's good. Why? First load case. What is first load case? All loaded maximum. So, this governing, this is the maximum. These are maximum. But when you draw the shear force diagram, shear is again maximum. So, this case 1 governs shear. It governs the bending moment over the support. Okay? It governs this. And then you have the second load case where you put this as maximum, this as minimum, this as maximum. So what will happen? It will go like this. Then you have the third load case where you put this as maximum, others are minimum, so you get now you have an envelope. And what we should do is we must redistribute the moments. Why? Because concrete behaves as a plastic material. Plastic material. Steel behaves as an elastic material. Later it will go into plastic zone. But our analysis is elastic. Oh, so in the analysis we have assumed we are here. Now how do you relate an analysis where we have assumed that it behaves elastic, whereas the actual structure it behaves plastic, which means this beam is capable of forming hinges at these positions and allow. So once it is formed, any extra load will be taken by a bending moment diagram like this, where if this is W1, this will be W1 L squared per 8. Any extra load. Until the plastic hinges are formed, it's like an elastic. Once the plastic hinges are formed, it will behave like this. So the codes allowed, BS code allowed it British code allowed it. So BS code allowed, Eurocode allows. You can reduce this moment up to 30%. Reduce this moment up to 30%. But I generally prefer about 10%. Easy. Otherwise, when it is more than 10%, you have to do extra. You cannot use the normal equation. You have to modify the design equation. So I generally prefer 10%. So what happens? I have a bending moment diagram going like that. I'm going to, let's say the value is 300. I'm going to design it for 270. And I'm going to design this for 270. Then what will happen to this moment? This moment should be increased. So how do you find how much to be increased? So what you do is you will draw a line here with 30 here, 30 here, and use this as a new origin of the bending moment diagram. Then what is this value? Let's say this has to be at about 220. Now what is the design moment here? 250. What is the design moment here? 270. You get a situation like this. But what is the more efficient section? So here it is cracked here and it's a rectangular section at the support. In the span, it's a flange section. So only this concrete is it. Lever arm is huge, very efficient. Flanged section. So what will you use? Okay, it's worth transferring moment from here to here. Why? This is very efficient, this is not efficient. And then when you are doing the concrete, now you are doing concrete like this, pouring from the top. And if you have a lot of reinforcement here or support, can you pour the concrete? No, you can't pour the concrete. Concrete doesn't go in. Now this is a construction problem. So it's worth redistributing the moment. And the most important thing you have to understand is we have a column, 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 the columns, a lot of columns. And can a beam fail here? If it cracks here, can it fail? No. Can it fail if it cracks here? Yes, no support. It can fail if it cracks. This will crack but no deflection. Here it will crack and it will deflect like this. So what is the best occasion to have a crack? At support. So no extra reinforcement at support. Why? If you put extra reinforcement, then you are going to hinder the concrete. Now, and because it's not going to fail, so no extra reinforcement is needed. It will never fail over the column. It will form a plastic thing, no problem. It's allowed. But where will it fail? Here. So where do you need extra reinforcement? In the span. Be little generous. So when you know it in the flange beam, you do all your calculations, simply reinforce because it's flange, and you need 3H20. You provide 2H20 plus 1H20. Why? Because even if the beam is overloaded, what will happen if the beam is overloaded? Which section will have a problem? Yes. At the support, it will form a crack. No problem. That is accepted. What will finally fail? The span. What is going to fail finally is the span. What are you going to do? You have to put little extra reinforcement in the span where it's going to fail. Will it ever fail? Even if it is overloaded. Bandhuka, will it ever fail? Will the beam ever fail?
No.
No.
No, sir.
Is that the way you have done the designs? You will provide extra reinforcement over the support. You will provide extra reinforcement in the span. Is that right?
Yeah.
You will not look at it this way. But this is the correct way of looking at reinforced concrete. So when I am designing, I will never provide anything extra over support. Just a calculated value. If I can say if there's a violation of 10 or 20 or 30 millimeter square, I will not even bother to do that. I will just provide even less, slightly less, because we know I can go up to 30% redistribution. I have done only 10% redistribution. So provide slightly less than calculated. Over support is accepted. Provided you have provided something extra in the span. Right? But that is not the way reinforced concrete is designed, taught. Always make sure you provide something extra at all sections. Is that right, Bandhuga?
Yes, sir.
Yeah, you will always provide something extra at the support, something extra in the span.
Yes.
But what is the safety? No safety. Because if something goes wrong, what you have provided extra is only little extra. But what I say is, provide something substantially extra in the span, because that's the section that's going to fill. Got it? So I have provided not just a little. I have provided 20 millimeter buys 340, 25 millimeter buys 490. So how would I detail that beam then? How would I detail this beam? Because if you look at the moments, it's likely that I will get 3 numbers of, so I'll get 2H20 and I will provide 1H20. I'll provide 1H20. Or it could be even 1H60. Now here I will provide 2H20, but here I will provide 1H25. Can you see how I detail the beam? Because I don't mind providing less here, because I am providing more here, and I am providing less in a less efficient section. This I am providing more in a very efficient section. I am providing more in a very efficient section. So which will have a higher increase in moment capacity. This will have a huge increase in moment capacity. Delta M is very big. Here the delta M is very small. So no point in providing anything. So provide less. Even if you provide less, the amount that you lose is very small. Whereas by providing more here, you are going to gain a lot. Anyway, you have to keep in mind that we have 1.35 DK plus 1.52. Huge assessment, and 1 kilonewton per meter square for partitions. Probably never comes. Maximum load of partition will be 0.5. So when you are designing, you have to be very practical, right? Think what are I doing, and provide the reinforcement accordingly. That way, you can do wonders with your designs, and your designs will be extremely economical, competitive. No person can come and do value engineering for your designs, and that's what we need from practicing engineers, because your duty is to give the best for the client. What is the reason? For doing some calculations, you are paid 1% of the cost of the structure. So the structural engineer's charge should be 1% of the total cost. Why? Because this includes supervision. Whether you have continuous supervision or periodic supervision, whatever it is, it's involves supervision. So you should not do any design for less than 1% of the total cost of the project. But if you are doing it for the structural cost, it should be at least 2% of the structural cost. Why? By doing it for 2% of the structural cost, as an engineer, you are going to save 20 to 30% cost. You tell the client, okay, you hire me, I'll save 20 to 30% in the cost, but you pay me 2%. Then you can see you are charging 10% of the what you see. And the saving cannot be done doing normal designs. You have to do special designs. Thinking completely out of box. Is that clear?
That is clear, sir.
So you can see these are new philosophy, right? Not a typical reinforced concrete design teaching that you always get at universities. It's far different. Even at MSc level, you would have learned at this kind of concepts, because now with Eurocode only we decided, okay, now time is enough, because Eurocode allow us to do a lot of economical designs by stretching the materials to the limit. So we are going to develop this. So this kind of things I was doing, but I thought we should bring it into the teaching, because initially what happens is we get engineers who have not seen even a structure or concrete. We have to teach them reinforced concrete design, so we struggled a lot with them because they don't understand most of the things we tell. So we have no time to tell all these important things. Then we get students for MSc, and some of them have forgotten most of the things they have learned at the university. So again, we can't do much. But later I thought, okay, now we cannot be complacent like that. We have to teach this. So that's why I thought, okay, let's teach the practicing engineers the mistakes that they do in design, so that they can start optimizing, and they can do the designs that nobody can ever do anywhere. So that's the target of this lecture series. All of you are to be regular designers, but nobody can do value engineering for your designs. So that's our target. Okay, Bandhuga?
Okay, sir. And sir, what can we do to take these value engineering tips and things to practicing engineers? I mean, from this lecture
No,
series.
actually now I'm one by one I'm going to disclose this a different way of thinking about structures. That different way of thinking is the one that value engineers use. So for a value engineer, a slab cannot be 150 or 170 millimeters. It can be anything like 130, 140, 150. And he will try his best to go for 130. So how much he saves? 20 millimeters each slab, 50-story building, 20 into 50, 1 meter. So he saves 1 meter thick concrete, having a weight of 25 kilonewtons per meter square. So what will happen to the foundation load? Will be reduced by 25 kilonewtons per meter square. Just because the engineer was smart enough to consider 130 as the slab, not 150. Because we are measuring with the tape. So tape has 10 intervals. Whether you use 130 or 140, always you can maintain. Right? So if you need 175, as just you look at it, so you try 150, 160, 170, and 180. Most likely it will be 160 that you can manage. Or sometimes you find 170. Sometimes you find because of deflection criteria and so on, 170 actually gives a more economical design, because it needs less steel, though they need little bit of concrete extra. The concrete is a very cheap material. If you save lot of steel, it is going to be cheap. So you can not do one calculation. You will do two calculations. One for 160, one for 170. Calculate the steel quantity with a rough detailed drawing, and then you decide whether to use 160 or 170 in this 50-story building. Why? Because if you save 10 millimeters, you are going to save 500 millimeters or 50 meters, 50 meters. So for everything, it is not one calculation. It's not, your task is not to find reinforcement. Your task is to find the optimum solution. And generally, engineers do not spend time finding optimum solutions. Why? Because they spend a lot of time finding the reinforcement. They find Z is equal to D 0.5 plus 0.25 minus K over 1.134. They do all these calculations. M is equal to 0.87 F by K A S multiplied by Z. So a lot of calculations I know. But how would I do it? MOBD squared, 100 days OBD is MOBD squared divided by 4 divided by 4, and I find the reinforcement. Yes, I don't spend much time because I don't spend time finding S. I have enough time to optimize. But that's why these shortcuts are so important, because I'm so confident that I can just get the answer by doing this. So I don't spend time finding the reinforcement. I spend time finding the optimum solution. But most of the engineers do is they spend a lot of time finding the reinforcement and they never bother to look at optimization. Is that clear, Luca?
Yes, that's clear, sir.
So you guys see why we need shortcuts. Because finding a reinforcement is a huge business for most of the engineers, not for me.
Yes, sir.
Right? From my phone, I can tell the reinforcement. Because on my phone, I can find MOV square. So how to find M? How to find M? I'll use a value like WS dot 10. I'll use a value like WS dot 11 in the internal space. I'll use a value like W squared over 9 when it is simply supported at 1 end. But no structure is simply supported like this. So even in this span, I'm going to get some fixity here. So I'll use WS squared over 10 here. Here also WS squared over 10. So I don't waste time finding the moment. On the other hand, if I want to find the moment, this is what I do. I don't worry about the full structure. I'll go for a substructure and put it onto SAP 2000 or Midas Gen. I'll put rollers here. Create this. Create this. Create. And then find the bending moment diagonal. And then I can do wonders. I can redistribute the moments just by looking at the moment. I can decide diagram. I can decide how much redistribution, because redistribution means changing the origin of the bending moment. So it's very easy, and I can find the moment accurate. On the other hand, I can find the moment approximate and quickly do a design. So somebody says, okay, I like to find the shear. So I find the maximum load multiplied by 0.6. That is the shear force. If somebody asks, what is the shear? I say, okay, it's 0.6 times the full load. On the other hand, I can find it from the bending moment diagram. The moment the model is there, you can find the shear force factor. Is that clear, Bandhu?
Yes, sir. Clear.
So what is the time now?
Now 8:20, sir. We have several questions, sir.
Yeah, so shall we answer the questions rather than going forward?
Yeah, okay, sir. And
well, I think I explained many things today, and the important parameter I'm going to share now. The important parameter I have to show is this magic number K. K has a magic number. K is a magic number. K has a maximum value is 0.167. 0.167. But when you remain MOBD squared below 3, this will never be violated. It will always be singular. How do I say all that? Let me look at this. Just give me one. Right. Now look at this. MOBD squared less than 3. What is 100 days of BD? No problem. There's 100 days BD value and it's single reinforced. Even if you go up to 4, you can still, if your grade of concrete is high, you can simply reinforce it. But a lot of reinforcement is needed. So that's why I like a maximum MOVD squared of about 3. Here, little reinforcement. When you go up, more reinforcement. So I like a value like 2.5 to 3. Even 2.5 is okay. Very little reinforcement. Can you understand that, Bandhuka? Why I have this magic number 3?
Yes, sir, it's a bit clear now.
Yeah, because with this 3, now I need this little reinforcement. If it's 2, even less. Why? Steel is a very expensive. So why do you want to save concrete when the expensive material is steel? Use less steel. Because when you use less steel, your structures are extremely ductile. They are very much under reinforced. They will give a lot of warning before failure. So they are good. Any structure packed with steel is not good. They are very expensive. So select large enough sections. What is the other advantage of selecting large beams, wide beams? You can do the construction easily. Most of the time, beams get honeycombs. Why? Somebody has selected the width of the beam as how much? 250 or 200. What happens when you cast? You can't pour the concrete. So the contractor might give you a phone call and say, can you send some teaspoons to pour the concrete? Because there's no space. Right? Got it?
Yeah, yes.
Okay, because you need a teaspoon to pour concrete. Why? You can't put vibrator. Why? The width is so small. So select a wide width for the beam. What is the main advantage? Shear capacity is high when the beam is wide. Very easy to do the construction. No honeycombs. No leaks. Because it has plenty of space. We can vibrate it properly. We can pour the concrete from above because reinforcement has sufficient gap. So we can, and the structure also very strong because it has high shear capacity. Got the point, Bandhuka?
Yes, sir. Got the point.
Is that the way you think?
That is correct. That is correct, sir.
Yeah, that is not the way you think. You think you are going to save with beam and select a thin beam. No. From which you save? Not from the beam, from the slab. Why? Each slab is reported 10 times in a 10-story building. So if you use 15 millimeters less, you are going to save 150 millimeters of concrete. But the reinforcement may be the same because most of the time 3D rules or 4D rules governs the reinforcement. Got it?
Yes, sir.
So there are many things we can do in slabs as well. But we need a very good QA/QC team. Now you can't do this with, just supervise. At least, you need HND type people who understand something. Or young engineers who are just graduating, who are looking for jobs. They are very good because they don't have much family commitment. It's their first job. They learn a lot about concrete structures with QA/QC engineers so that they can become better engineers one day because they get a lot of construction experience without carrying the burden of project management. Otherwise, you hire a construction engineer and that person has to carry a lot of burden as construction manager. Whereas you get QA/QC engineers, they have less burden because they are not doing management, they are assuring the quality. So they can learn a lot and there will be huge boost to the construction manager. Why? Now he need not be looking at the construction. He can do the construction management part rather than doing the construction engineers part. So otherwise what happens in Sri Lanka is you hire one guy, he's paid a big salary. He's supposed to look after the construction management part. He is supposed to look at the QA/QC part. He is supposed to do everything. And after a few years, you find you have a wasted engineer. Why? That guy has tried to do too many things, and his efficiency is very low because that guy is trying to do too many things. But so that is not the way it's operated in other countries. They use a lot of engineers. And they are paid a reasonable salary, not a very high salary. They are paid reasonable salaries. They all work together. and they rise the ladder, and as they rise the ladder only they will get high salaries. But that is not the way it operates in Sri Lanka. We get few engineers, we expect them to do everything. That is not good. But that is not the way Altair was constructed. Altair had a big team of engineers, and they were doing the QA/QC part in addition to they were engineers for everything, right? And the quality of construction is very high. So that's the way you have to look at it. Is that clear?
Yeah, that is clear, sir. I think most of the construction companies not having this QA/QC department. Some companies are having that, I think.
No, actually, QA/QC can come from the client side because QA/QC can be independent.
Yes.
So the construction company also needs a QA/QC side. But in addition to that, QA/QC can come from an independent consultant. Consultant's QA/QC also should be there. But it can be client's QA/QC because client is the one who wants it properly done. So client will be willing to spend little extra money to make sure things have happened properly, and he has a proper record of what this contract has done. So you have to educate the client to spend on QA/QC. That is a good way of thinking. Look at it. Okay.
Okay, sir.
So you have to educate the client. You can say, okay, you have a QA/QC department, and as the consultant, I will manage it. But I can't pay the QA/QC engineers. You pay, but I'll manage it, right? And for a small fee, I will manage it. But part of my 1% fee, I'll manage it. But QA/QC engineers' salary is your business. And in the contract, you would say so many BSc, so many chartered engineers, then so many BSc engineers, and so many QA/QC engineers in the contract. So the contractor is forced to cost it and include it in the bid. Because when you go for competitive bidding, you will find that contractors give a lot of discounts because they have machinery, they have a lot of things that they don't have to hire. So all this wealth that they have, sometimes they have scaffolding, they have plants. So the cost of hiring is very low for them. So they have already depreciated those plants and machinery and their equipment on their balance sheet. So basically, it's coming almost free of charge for them. Whereas when you are finding the rate, all those are included. So contractors will also find that they can offer pretty good rates, especially because they are getting everything without VAT. So there are so many things. So you'll find when you hire a big company, when you are a smart engineer, you can bring things down drastically. And so that is something that I did recently in a project where the allocation for the foundation was 595 million. The original geotechnical engineering report produced a foundation of 800 million. Now we might give the contract for about 400 million. My plan is to further optimize it while we are doing it, so that we might hit something like 360 or 375 or 380 million. So just imagine one doing a job of 800 million for 380 million. Have you ever found that kind of optimization? Bandhuga?
No, sir.
No. But that's what I do. In Eurocode at the flyover, the cost was 750 million. We did it for 500 million. Right? And Nigambo Hospital, they were planning to demolish the existing 8-story building and construct a new building with all the medical equipment coming new. The cost was 10,500 million. I completed the whole project for 600 million, giving an extra space of 58,000 square feet. So just imagine 10,500 project was brought down to 600 million, right? And then I have done a bridge at Mahiangan, 300 feet long, 10 feet wide. 300 feet long, 10 feet wide, cost was 6 million rupees in 2012. So that's the kind of value engineering you should be thinking, because value engineering is our future, but it cannot be done with conventional thinking and the type of reinforced concrete design or other designs that is taught at universities. We can't do it because we have been taught the subject, not the application. So application is can be very different. So that's why there's a lot of room for value engineering in every project that is undertaken in Sri Lanka. And I can even if you talk about Altea, I didn't design it. I already checked it by creating a model. And if I design Altea today, the total weight of Altea structure can be brought down to 70% of its weight, which means I can do the Altea construction for 70% of its original cost. Have you ever thought that that type of optimization is possible in an intentionally designed structure?
No, sir.
Bandhugar? Huh?
Can't believe, sir.
Yes. Can't believe this. It's possible. If you want, I'll tell you. Towards the end of the lecture series, I'll show you how the Altair can be designed to weigh 70% of what it is today. So that's the final thing I'm going to. I'll wind up one day. Might need 25, 30 lectures, but the final day I'll show you. So keep that in mind. Ask that
Okay,
question from me, right?
Okay,
and I will show you, right? So what are the questions?
Yeah, there are only there are 4 questions. One is a bit long question. I will read, sir.
Yeah.
Uh, if the load of the slab distributed to beams as per yield line pattern, is it reasonable curtail bottom reinforcement close to the corners of the slab? On the
actually in two-way spanning slabs, no engineer practices this in Sri Lanka, but there's something called all the moments that you calculate based on yield line method is applicable only for the middle strips. End strips is not applicable. End strips is a nominal reinforcement. And no engineer in Sri Lanka practices that, but by practicing the edge strip, middle strip method, you can save a lot of steel in a slab. Okay, Bandhu, that's the answer, right? So I'll be covering that later, but so don't worry.
Okay.
Of the steps I'll be.
There's another, I think it's like a comment. I trust that for flange beams, neutral axis should be within the flange to get the benefits of flange action.
Yes. So next week, my topic will be flange beams. So don't worry, I'll answer next week.
And the other thing is, sir, could you explain us the workflow in a BIM environment? I think he's referring to building information modeling.
Yeah, information modeling. Yes.
Yeah, BIM
so
environment.
basically that is 3-dimensional modeling and a lot of data, but I'm not talking about that level, because first thing is you have to get the building right.
Yeah, he's asking.
BIM is only a database, right? BIM is only a database.
Okay.
So in design, there are 2 levels. The first level is preliminary design, where wealth of experience should come in. And at that level, BIM can't do anything. But once you design, start producing the drawings, BIM can do a lot of things by coordinating among all the people who are involved in the project. Right? BIM can't do anything at the level that I am talking.
That's what he's asking. He's asking BIM environment, can it be done at this structural design stage, something like that?
No. Now, this is the initial stage. Now, we are trying to get the numbers right.
Yes, okay.
At the level that you are going to get the numbers right, BIM can't do anything, because BIM is a computer tool. Whereas as humans, we can think. Computer can't think. Computer can coordinate. So BIM is good for coordination. But now we are still at the infancy, that is preliminary design stage, where we are going to get the numbers right. And numbers right is a game where we use the brain. So that part cannot be done by computers. Right?
Okay.
Computers, once we do that part, we get an optimum solution. Coordination of the construction activities of this optimum solution can be done by the computer. That is the BIM. Got it?
Yes, got it, sir.
Question.
There's one last question. if we expect some amount of shear force in a beam, like 100 kilonewton, using that value, how can we do the flexure and compression reinforcement in a beam? I think
that is some topic that I'm going to cover shortly, because shear design, there's a special way you have to think about it. So I'll cover, don't worry.
okay, sir.
In the next few lectures, you will learn all that.
Okay, sir. Okay, sir. I think that's all questions. Then I would like to.
So actually, I'm going very slow because I just want to get you to think different.
Yeah, that's better, sir.
Yeah, because getting you to change the way of thinking is not an easy task.
Yes, sir. And also, I thought, sir, that this value engineering part, that is very, I felt it is very important. So, what can we do to take this to practicing engineers in a more efficient way? We are doing this.
No. What you have to say is, you individual now they have been 144 engineers today.
Yes.
And there will be many more who will go through this lecture when it is available on YouTube.
Yes. Okay.
Now, if all of them start doing value engineering, those who are not doing value engineering will have no place.
Okay.
Right? So that's how it goes. So, and also you tell the client, okay, you get a design done by a normal engineer. I'll pay his fee. Then I'm going to do value engineering, reduce that fee by 20% or 30%. You pay me that, 10% of that, and I'll pay that average engineer's design fee. Because when you are in a 5,000 million, let's say 5,000 million big project, 30-story or 40-story building, right? It will cost 5,000 million, right? And you are going to reduce the cost of it by 40%, structure's cost. So make it, so in a 5,000 million project, 2,000 million will be the structure. Out of 2,000 million, you save 20%, sorry, 40%. So you save 400 million, right? Whereas the design fee is 5 million, sorry, 50 million. So you are saving, sorry, I got the wrong. Say the whole project is 5,000 million. Your structure is the structural cost is 2,000 million, and the structural engineer is going to charge 2% of that. Structural is going to charge 2% of that. That is 40 million, right? So structural engineer is going to charge 40 million, right? But if you are doing this, you will charge not 10%, because you might charge about 20%. And so 2,000 million project, you are going to save 40%. Then you are saving 800 million, right? And even if you charge 10%, your charge will be 80 million. So even if you pay that engineer 40 million, it's worth, because you are going to get 40 million anyway. And client is going to save how much? 800. Have you got the point, Pandu?
Yes, sir, I got the point. Yes.
So you can pay the engineer's fee also by doing value engineering. You can say, okay, you get this done by any engineer in the field, right? So he gets the job done because he has no cost, and you cost it properly. Then you do the value engineering, save everything possible, and then you pay that engineer, average engineer, his fee, and you keep the rest. Who is the winner? You are a winner. That engineer who has done the job is also a winner. Client is also a winner.
Yes, sir. Okay.
Not only that, because client will have a QA/QC department under his, paid by him with the savings. Now young engineers will get jobs.
Yes.
As they pass out, they will have jobs. Plenty of jobs in the industry. Who are the winners? Everybody is a winner.
Yes, sir.
Got it?
Got it, sir.
Okay, so let's think differently.
And I would like to invite Civil Engineering Sectional Committee Chairman, Engineer Mangala Silva, to do the vote of thanks and wind up the session.
Yes, sir. Sorry that actually I couldn't participate at the very beginning. I couldn't log into that one. Once again, I would like to say thank you very much to Professor Jai Singh. And Professor Jai Singh has mentioned something about he's willing to do a value engineering at the end of the session. I think, sir, we can arrange a physical session for that one.
Yes, yes. Okay. No
So
problem.
I think that could be the most interesting thing. So when you are ready, please let us know. We will arrange the physical
No,
event for that one.
the rate
That is
we
I
are
think that is
going-
how the value comes, right?
Yeah, no,
So-
at the rate that we are progressing, we might need about 35 to 40 lectures to finish this.
Yeah.
Nearly 8 months to finish this.
Yes, it's all right. I mean, when we're ready, maybe we don't need to stay until end of the lecture session. So when we're ready, sir, you let us know. We will arrange a physical lecture, right?
Okay.
And also, I want to say thank you to Kamala Madam at the very beginning, her inputs for this lecture series. Thank you very much, Madam. Thank you very much, sir. And at last, not least, but I want to say thank you very much, Bandhuka, for organizing this everything. Thank you very much. Good
We
night.
are really thankful to Bandhuka because he organizes, he coordinates everything next year.
Yes, sir.
Next day lecture will be flange beams.
Okay.
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 Design of flange beams. Right?
Okay.
Professor Jai Singh, I am Vijay Ratna from UK. Thank you for
Ah,
all your.
yeah.
Yeah, I am the one who posted that the flange beam case. I just want to say, I was just trying to catch you sometime, but I miss you.
Yeah. So
it's very good lecture. Very good lecture.
Is this Mr. MD Vijay Ratna? Start
Yeah.
Ah, sir. It's after a long time.
So I was lucky to find time to participate this lecture. The reason is today I am sick and at home, so that is why.
Right. But you can download, watch it, Vijay.
Yeah, definitely. Yeah. I this time I came last December. I went to university to look for you, but I couldn't find.
Right. No, I'm at Piliyandal now. So anyway, I knew Vijay from 1987. He was 7 years senior to us at university. Is that right?
Yeah, right. Yes. Professor Priyanda is batchmate.
Yeah. Okay. Yes.
Once in a way, I'm following up some lectures, so all that,
No, you can actually try my YouTube channel, Advanced Computer Modeling of Structures, which contains so many videos on computer modeling and all that. Advanced Computer Modeling of Structures on YouTube.
Okay, that is what my new subject is. I'm also in the advanced analytics team of WSP, doing all high-end products like cable structures, vibration analysis, fatigue design. Those are my subjects now.
Yeah. Okay, so you can actually try MTR Jai Singh, Advanced Computer Modeling of Structures. Type my name and then type Advanced Computer Modeling of Structures. That's my YouTube channel now for computer modeling stuff. You can learn a lot by going through that.
Yeah, definitely. Definitely. Thank you very much for your kind cooperation and all. Very nice lecture, and it is very this thing. Value engineering is a very valuable field here in UK either.
Yes.
Yeah. Okay. Thank you.
Thank you very much.
And a great time. I'll catch you once again.
Yeah, Mr. Vijay Ratna ran Stat Consultants until he left Sri Lanka in 2000 something. Is that right, Vijay?
2006, yes.
2006, yeah. Okay then, thank you very much.
Glad to hear your voice again.
Yeah, thank you. I do.
Okay, thank you for allowing me to talk. Thank you for allowing me to talk.
I also, Mr. Vijay Ratna followed our first MSc batch, 1995. 96, and he did MSc also with me under my supervision on
high-rise buildings and wind engineering. Yeah, and wind and seismic engineering.
We have a paper on ISL which is used by engineers on the wind behavior, dynamic behavior of tall buildings under wind. And it was published in 1998. Transactions.
I have done a massive building in Iran, so which is highly seismic, and I definitely every time I can remember what you
So
taught me.
Vijay, are you in a position to share a lecture for us with
What kind of a subject?
No, whatever subject you feel comfortable, we are willing to listen to.
Yeah, generally I am doing a lot of fatigue design, vibration analysis,
So
and
you can the vibration analysis, fatigue design is a very good topic for Sri Lankan engineers. So if you can do about 1 or 2 lectures under this series, it will be very helpful.
Okay, we'll try. Yeah.
Okay.
Okay.
Okay then. Thank you very much.
Okay. Is your telephone number still the same?
Yeah, same number.
Okay.
I'm on WhatsApp also. You can try that number and send me your WhatsApp number.
Okay, I will send an invite. Okay, thank you. My God, I am very pleased today that I was able to catch you.
Yeah, okay, right.
For last so many years, I was just trying to struggle. I didn't come, only came only 4 or 5 times to Sri Lanka. Every time I miss you. I'm very sorry.
Right. Yeah. Okay. Right.
Yeah, okay. Thank you.
Yeah. Okay. Thanks.
Okay,
yeah.
Wish you all happy new year.
Yeah, we all wish you all a very happy new year. I forgot to tell that. Because today is a sad day, because my research supervisor in Cambridge has just passed away this morning. So, not a good day, because he was a brilliant bridge design engineer called Professor Chris Burgoyne. One of the best in the world. Yeah.
I have met him here once.
Right. Yes.
Yeah, long ago, about 10 years ago.
Yeah. He retired in 2017, and by this time he's about 73 years.
Yeah, maybe.
He retired at the age of 67, only 73, but he was a very healthy man. Suddenly he got some problem and passed away.
Yeah.
We really don't know what is the exact problem, but just admitted to the hospital within 1 or 2 hours, he has died. So
he's lucky person without suffering.
Yeah, he's a lucky man. Yes.
Yeah.
Yes. Okay then, thank you very much.
Okay, thank you all very much. Very kind of you. Okay, bye.
Okay, I'm leaving now.
Okay, sir. Thank you. Thank you very much.
Thank you very much.